Okay, dear students, let's have another conversation today. Let's have another interaction today, and today we will try to go to uh, some fundamental level in our syllabus. That what we have to talk about is we would like to talk about an idealized quantum well. So this is something that we would like to talk about. Idealized uh, quantum well. And you can use this book if you are interested. This will be available in the library. This is C. Deller and M. Lano, Nanostructures, Theory and Modeling. I'll be using this book to have a discussion on this idealized quantum well. Now, real materials are real in a sense. They have dimensions. Okay, so if we talk about the three-dimensional material, it has three dimensions: X, Y, and Z. As I said, if we rightly think about a real material in terms of its dimensions are such that the electrons living in these materials never see the boundary of these materials, right? So when electron never sees a boundary, its potential is continuous and its energy leads to the formation of conduction band and the valence band, as long as the band theory of solids is concerned. But if we constrain a material, if we constrain the dimension of a material, its macroscopic behavior changes to the microscopic behavior. The behavior of the electron becomes somewhat mixed. Why it becomes somewhat mixed is, suppose I have something having all the three dimensions, okay, X, Y, and Z. Here you have a complete framework that you can talk about, and this framework would lead us to the bands in the solids, right? And you have the motion of electron in such a way that its behavior is symmetrical. Because when you discuss the theory, you discuss it in terms of an idealized system. And the targets that we live with are crystalline solids. And what are crystalline solids? Crystalline solids are those materials in which the electron will experience the same kind of environment from point A to point B. Within that, those infinities in which this electron is living, it will have some periodicity, and it is that periodicity of the electron which is exploited in terms of the Fourier transforms, and you come up with the band structure of the solids, right? But if you decrease the dimensions of your sample, now you have a three-dimensional sample, and you decrease its dimensions. If you decrease its dimensions, you have three kinds of systems that will automatically evolve out of it, provided the length of the dimension that you go is of the order of nearly 1 to 20 nanometers, right? So if I have a three-dimensional box and its X is large, its Y is large, and its Z is of the order of, say, 1 to 20 nanometers, what you are doing is basically you are confining your system. Even though X and Y are same, right? They have the same macroscopic properties. They have the same periodicity. They have the same block function that will describe the motion of these electrons. But when you are making a constraint along Z direction, now you have a mixed kind of situation. Are you getting my point? You have a mixed kind of situation. You have a situation in which you will expect quantization along Z, and you will have the normal behavior along X and along Y. Right? This is what is called as quantum well. We call it
Quantum well.
quantum well. Now, if I make a constraint, the constraint that I was talking about, if I make a constraint along X of the order of 1 to 20 nanometers, along Y of the order of 1 to 20 nanometers, along Z there will be no confinement. What you will get? You will get, first you got what? First you got quantum well. You got quantum well. And now you will get the quantum wire. Isn't it? Because you are constraining X and Y of the order of 1 to 20 nanometers. So you have confinement. Your system is an amalgamation of the quantized rules along X and Y, but no quantization along Z. The material that you will obtain is what's called as quantum wire, isn't it?
Yes.
So again, you have some kind of mixed environment now, because your electron is certainly propagating. It's going through these periodic motions. It's going through these block functions, but its Y and its X and Y are experiencing quantum confinement. So here again we are using the word confinement. So when we talked about the quantum well, what we did, we confined one dimension of the sample. And you have a mixed system where you will have the original propagation and a propagation that is constrained by virtue of the confinement, isn't it? And you will have the third case. What's that? If you decrease X to 1 to 20 nanometers, Y 1 to 20 nanometers, and Z 1 to 20 nanometers, what you will obtain is called as the quantum dot. This is also called as artificial atom, quantum dot. So quantum dot will exactly behave the way an atom is behaving under certain approximations. This is the argument, okay? Getting my point?
Yes.
So you have these three categories, but they are all technological in nature. People obtain these conditions in the laboratories, okay? They obtain their samples which have confinement along Z, which have confinement along X and Y, which have confinement along X, Y, and Z, leading to what's called as quantum mechanical confinement. And you have a different branch of science here, what we call as nanostructures, right? So what's our target here today is that we want to talk about this quantum well. We want to choose an idealized quantum well, isn't it? So quantum well is clear. What is a quantum well? So if you have a quantum well, and you will probably you will look for the experimental ways of obtaining the quantum well, where you will certainly encounter these semiconductors, the direct band semiconductors like gallium arsenide. And these are the materials in which people are trying to obtain these wells. So to start with, to discuss the quantum well, if I go with the generalized wave function, I go with the generalized wave function, say psi of r. And this psi of r will look like uk of r, and I will use another eigenfunction phi of r. Right? So this is our wave function. This is basically the solution of the Schrodinger's wave equation, which has a dependence on uk of r. What is this uk of r? This uk of r is the block function. And now your psi has an incorporation of both types of things. Because we're talking about the quantum well, your Schrodinger's wave equation must have a structure made of kx, ky, and kz. And for kx and ky, your original quantum mechanical work that you have already done is valid. And for the z part, you have and for the z part, what you are expecting is, you are expecting the confinement. And the confinement is leading us to the quantization. So if this is the solution of the Schrodinger's wave equation for an idealized, see, I'm choosing an idealized system because real systems are very complicated. There are lots of impurities in the real systems. So I'm trying to cross the message through this idealized quantum well. So what should I do is I should write down the Schrodinger's equation. So how will my Schrodinger's equation look like? It's minus h bar square by 2m. But this m cannot be m. This m has to be m star. Because m star will certainly depend on the type of material that you're talking about. Different materials have different types of coordinations. They have different types of screening available in them. So in different materials, your particles will have different masses. Even though that difference is extremely small, but extremely small is also very important in the field of physics. And then you will have del square and phi of r, and then you will have plus. You are working in 3 dimensions, but 2 dimensions are macroscopic in nature, and the 3rd dimension is microscopic in nature, right? So that means here I would like to write down V as V confinement. See, the nature of V along X is periodic. The nature of V along Y is periodic. You have exploited all those brilliant zone kind of things, and you have made all the calculations based on that. And this V is what? This V is becoming important. And I call it V confinement. And this confinement is because of what? Because of choosing the 3rd dimension of the order of 1 to 20 nanometers. Are you getting my point? Your system is an amalgamation. Your system is in some kind of superposition between a pure quantum mechanical nature along Z and quantum mechanical nature along X and Y, but the boundary conditions are very different, right? So this is equal to, I'll call this, say, E phi of R, right? So this is my generalized Schrodinger's equation for a quantum web. And this V is giving us the understanding of the confinement. And in our problem, we have confined only one dimension of the sample, right? Now, I would look for the solution. Now, how will I write down the solution of this equation? So if I choose phi of R, okay, is equal to, see, my solution should incorporate all the three, right? I would like to incorporate X, Y, and Z. What can I expect here? I can expect here something like 1 by under root of, I will call it L, e to the power of I, k dot, let me call this zeta, and this is in the form of infinite boundaries for the electron living along X and Y, and another part I will choose as zeta n of Z. See, the confinement is along Z direction. For that, the solution is zeta n of Z. And this part should give you the information about the solution in terms of X and Y. And this is exactly what we have already done. So let's think about these symbols. What should be this L? L is the function of Lx and Ly. It should be. You know that, huh? Okay? You know these things. And then this K, what we call as K vector. What this K should be? It should be the function of Kx and Ky. It is not the function of Kz in this case. It is the function of Z in this part, because this part is leading us to the confinement. And this part is leading us to the original way of assuming an electron in an infinitely long periodic system, in which you have two domains, domain X and domain Y. And what should that zeta be? So in general, what you have here? You have here K dot R, and R for X, Y, and Z. But here, R for only X and Y. So this zeta, that's why I have written here zeta, in order to avoid a generalized R. So this zeta will be the function of what? It will be function of X and Y. Right?
Yes.
Is this clear? Okay. Now this part is done, and this part is also done. This part is because of confinement. Okay? This is the solution to the Schrodinger's equation in terms of the confinement, where the dimension, the Z dimension of your sample is of the order of nanometers. Okay? And this is reflecting that part. And this is reflecting the macroscopic part of the Schrodinger's equation. Isn't it?
Yes.
Are you getting it? Okay, fine. So now for this I can have Schrodinger's equation. What will be that?
Sir, 1 minute.
Yeah.
सर ये है यहाँ पर का ईटा ये वाला
This?
ये माइक्रोस्कोपिक है कि मैक्रोस्कोपिक
This is this is because of the confinement.
है
The dimension is, it is microscopic. You can think it in terms of that. Okay? So what we have is for zeta, what can I write for zeta? I can write minus h bar square by 2m star. A star will make it different. Star is telling you that you are in the field of materials, right? You are moving away from atoms. Your atoms are living in materials, and M star is a reflection of that. And this del square, its first two parts are taken. They are solved. They are resolved. Okay? And what is remaining is d2 zeta n of z by bz2. Then plus v confinement. Are you getting? Okay. Chi of z equals en of chi of z. Right? Fine? So this is your Schrödinger's equation for the confinement. You are looking for a very complex system because it has two macroscopic domains and one microscopic framework. Are you getting my point?
Yes, sir.
And we are trying to realize it ideally. We are trying to realize it mathematically, isn't it? And this is a very known equation to you. Okay, you know this is an equation that you know its solution, and what my choice is, my choice for this V confinement. V confinement, I will choose 0 if my domain is from minus Lz by 2 Z Lz by 2. Right? This confinement potential is treated as 0, and this V confinement is infinite otherwise. Right? So you have boiled down to a very one-dimensional Schrödinger's equation. In addition of the two solutions that are available for x and y. Are you getting my point? So, what do you expect? You know the solution of this differential equation. The solution of this differential equation will give you what? It will give you En is minus h bar square by 2m star kz square. Can you tell me what is kz? Yeah? Come on, what is that? What is that? That is n pi by Lz. So this is your quantization. That is minus h bar square by 2m star times n pi by Lz. It has to be square. Yes, you're right. Okay? You have, what you are getting? You are getting the bands. You're getting the bands. You're getting the bands. Somebody is calling me. I think I'll check it out. Hello? Ji, you just come to physics department. You go into the HOD's room. There is your parcel. Okay? I'm right now busy in the class. Okay. Okay, so I thought it might be important. Okay, so this is your quantization of energy, and you will have the solution. You will have two types of solutions. You will have odd solution. You will have even solution for this problem. How will that solution look like? Yeah, you can have chi n of z equals, yeah, come on, do you remember? Under root of L z by 2 sine of n pi by L z and z. This is for even. So this will lead us to the even solution, and for odd you will have, yeah, under root of L z by 2, then you have cosine of n pi by Lz of z. So this will be for odd solution. Right? Right? Clear? Now what am I trying here is, I'm trying to write down a generalized form. Right? So I'm trying to write down this formalism in such a way that it can give me a complete mathematical form. Isn't it? Are you getting my point? Okay. Now what you expect from here is, check this out. Okay, the whole story is in front of you. Now, if I choose this h bar square pi square by 2m star L z square, if I choose this thing nearly equal to 150 millielectron volt, okay, I choose this thing nearly equal to 150 millielectron volts, and I choose this Lz. What is Lz? It's the confinement length. I choose this Lz nearly equal to 100 angstrom. Okay, and m star. What is m star? This is the effective mass. Okay, if I choose this effective mass as 0.1 times the mass without any kind of constraint. So what it leads basically, okay? What it leads is that this 2D confinement leads to the formation of bands. You will see it, what it leads to. It leads, I would like to read it from here. It leads to bands at each energy. And each energy, you know that quantization, okay? That I wrote down previously. And the energy that you have, what is that? That is h bar square k square by 2m star. In a subband corresponding to the kinetic energy for the in-plane motion of the carrier. What does it mean basically? You have a 2D confinement, okay? Your confinement is governed by two set of models. A model that leads to that periodic motion of the electron, and a model that leads to the quantization. So what you expect? You expect here bands. You expect here a band kind of thing. And what is the basic way of realizing these bands is density of states. It is the density of states. And so what it says, the effect of confinement or the electronic structure is evidenced in the density of states. That is, what is density of states? It's number of energy levels per unit energy range. So the density of states that we write down for this system, if I choose the density of states as rho, I will call this, say, rho 2D. Rho 2D is what? The density of states. It is equal to 2 times sigma of del of the overall energy minus the energy along Z minus h bar square k square by 2m star. This equation is giving me the combined density of states for this idealized two-dimensional system. Are you getting my point? Now the question arises, why there is 2? The 2 has been introduced here for the spin of the electron. The spin of the electron has a degeneracy equal to 2. That's why 2 has been incorporated in this equation. Isn't it? Are you getting my point? So, if you take out the quantization part from this equation, you will go back to the original solution, a three-dimensional solution that you have already obtained in the course of solid state physics, isn't it? Okay, so this equation gives me a combined mathematical formalism of density of states. And what it tells me that your system has density of states. It has two types of density of states. One is stair-like. And stair-like is coming out of confinement. It's coming out of confinement, and you have another part that is coming because of X and Y, and this dotted line is telling you about the density of states, and these density of states are continuous for X and Y, but in the but due to the confinement along the Z, there is a staircase like of structure, isn't it? Are you getting it? Okay, so I would like to give you a quick revision of this, if I can connect it. I don't know. Come on. It's not coming like that, huh? Okay, it's like this. Okay, so the main thing that the main thing that I focused in this lecture is the confinement. Okay, that was the basic idea that we wanted to exploit, and we have written down the density of states for a combined system for an idealized quantum mechanical well. So the first point is quantum confinement. So what is quantum confinement? And you can read it. When a particle such as an electron is confined to a very, very small region comparable to the wavelength of de Broglie wavelength, okay? So what you automatically expect the quantization of energy levels. So this is what is called as quantum confinement. Now the question is why it occurs. It occurs at the very small scales, at nanoscales. And what happens here? Electrons cannot behave like free particles. So along X and Y, your electrons are treated as free particles. Are you getting my point? They're treated as free particles, and boundaries restrict the motion leading to the discrete energy. So it has a lot to do with the problem of particle in a box. Okay, so quantum confinement is often, you will see I have given you the solution for the confinement part in terms of the particle in a box. I wrote down the Schrodinger's equation in that format and wrote down the solution of Schrodinger's equation in the similar fashion of particle in a box situation, and where you have energy levels, and these energy levels depend inversely on the square of the size of the system. So as the size of the system decreases, the spacing between the energy levels, are you getting it? If the size does not decrease, you're not able to differentiate the two energy levels. You have an energy band, you have a valence band, and you have a conduction band, isn't it? Okay, this is what we are trying to emphasize here. And you see a general graph here. This graph shows how ground state energy increases as the confinement goes on. Okay, so you can see the rise and the fall of this energy. So, as I said, dimensional confinement changes. What it changes? It changes the density of available electronic states. And you remember the density of states that I wrote down for the quantum well, that's comprising of the energies that these electrons possess being free along X and Y and being confined along Z direction. Now this can be a generalized graph. Basically, there has to be that stair kind of thing. But here is a generalized argument that you can see this blue line. The blue line is talking about the bulk material. This is the density of states for the bulk material. Okay. Then you have the pink. It's almost constant for the 2D materials. But as we saw, it has the existence of these sub-bands. Okay. And then this green line is an indicator of it's the generalized behavior of density of states. And as we saw in case of quantum wells, there is the existence of sub-bands where you have those stair kind of structure for density of states. Okay. So examples, you might have heard about the quantum dots. Okay, so what quantum dots are? They confine electrons in all 3 dimensions. They're used in displays and biological imaging. Okay, you can image the molecules, the blood molecules. Okay, using these quantum dots. As you rightly remember, I told you in the beginning that a quantum dot is also called as an artificial atom. You have the examples of quantum wells and quantum wires. Quantum wells confined in 1 dimension, as you know, as I told, and wires in 2 dimensions. They are very important in semiconductor devices. Their main applications include lasers. Okay, so you see the application is coming in lasers, in LEDs. Yeah. Application of these materials in which you have these quantum confinement kind of thing going on. Okay, quantum computing, it has a role, components, and nanoscale electronics. So to conclude this talk, what I have is quantum confinement explains many unique properties of nanomaterials and plays a key role in modern nano. So it's a very, very important and basic mathematical model to give any kind of explanation for the new materials that you may be preparing in the laboratories. Okay, so this model will be very helpful. But all you have to do is to incorporate the material domain, the type of experiment that you are performing. You will certainly have the results that you will be looking for. So with this, I would like to thank you all. If you have any questions, you can ask me. Right?
Sir, how the energy levels increases when we reduce this?
Because it has everything to do with an atom. When you see the atom, when you solve the problem of hydrogen atom, say for example, what you obtain there? You obtain selected energies for electron. Electron cannot have all possible energies. It can have only some discrete values of energy, right? So here, when you are confining it, now you are not talking about an atom, even though you are talking about the number of atoms, but the number of atoms is only up to 100 atoms, okay? Up to 100 atoms, when you go to that domain, you find that the similar kind of behavior. You find quantization. You have steps in the energy. The energy is not continuous, as was expected for a bulk material. For bulk material, the energy is continuous. But in bulk materials, what you are able to do is you are able to differentiate a band as a valence band from the conduction band. And then you have a forbidden band. The electron or a hole will not exist between the bands, right? But there you have infinite number of atoms. Okay, that's a macroscopical system. Okay, so there you have continuity in the energy, and here you have quantization of energy. That's why a quantum well is basically the mixture of continuation of energy and the quantization of energy. That means it has to be a mixture of the continuation of density of states and quantization of density of states. That's how it goes on. Okay? So thank you all.